The graph isomorphism problem is the computational problem of determining whether two finite graphs are isomorphic. Besides its practical importance, the graph isomorphism problem is a curiosity in computational complexity theory, as it is one of a very small number of problems belonging to NP, neither known to be solvable in polynomial time nor NP-complete. It is one of only 12 such problems listed by Garey and Johnson, and the only one of that list whose complexity remains unresolved. It is known that the graph isomorphism problem is in the low hierarchy of class NP, which implies that it is not NP-complete unless the polynomial time hierarchy collapses to its second level. At the same time, isomorphism for many special classes of graphs can be solved in polynomial time, and in practice graph isomorphism can often be solved efficiently. This problem is a special case of the subgraph isomorphism problem, which is known to be NP-complete. It is also known to be a special case of the non-abelian hidden subgroup problem over the symmetric group. State of the art. The best current theoretical algorithm is due to Babai and Lux, and is based on the earlier work by Lux combined with a subfactorial algorithm due to Zemlyachenko, Kornirenko and Tishkevich. The algorithm relies on the classification of finite simple groups. Without CFSG, a slightly weaker bound 2.0 was obtained first for strongly regular graphs by Laszlo Babai, and then extended to general graphs by Babai and Lux. Improvement of the exponent square root n is a major open problem. For strongly regular graphs this was done by Spielmann. For hypergraphs of bounded rank, a sub-exponential upper bound matching the case of graphs was obtained by Babai and Kodinati. In 2015, Babai announced a quasi-polynomial time algorithm. On a side note, the graph isomorphism problem is computationally equivalent to the problem of computing the automorphism group of a graph, and is weaker than the permutation group isomorphism problem, and the permutation group intersection problem. For the latter two problems, Babai, Cantor and Lux obtained complexity bounds similar to that for graph isomorphism. There are several competing practical algorithms for graph isomorphism, due to McKay, Schmidt and Druffel, Ullman, etc. While they seem to perform well on random graphs, a major drawback of these algorithms is their exponential time performance in the worst case. Solved special cases. A number of important special cases of the graph isomorphism problem have efficient, polynomial time solutions. Trees, planar graphs, interval graphs, permutation graphs, bounded parameter graphs, graphs of bounded tree width, graphs of bounded genus, graphs of bounded degree, graphs with bounded eigenvalue multiplicity. K-contractible graphs, color-preserving isomorphism of colored graphs with bounded color multiplicity as in class NC, which is a subclass of P. Complexity class G. Since the graph isomorphism problem is neither known to be NP-complete nor to be tractable, researchers have sought to gain insight into the problem by defining a new class G. The set of problems with a polynomial time Turing reduction to the graph isomorphism problem. If in fact the graph isomorphism problem is solvable in polynomial time, G would equal P. As is common for complexity classes within the polynomial time hierarchy, a problem is called G-hard if there is a polynomial time Turing reduction from any problem in G to that problem, i.e., a polynomial time solution to a G-hard problem would yield a polynomial time solution to the graph isomorphism problem. A problem is called complete for G, or G-complete, if it is both G-hard and a polynomial time solution to the G problem would yield a polynomial time solution to. The graph isomorphism problem is contained in both NP and COAM. G is contained in NLO for parity P, as well as contained in the potentially much smaller class SPP. That it lies in parity P means that the graph isomorphism problem is no harder than determining whether a polynomial time non-deterministic Turing machine has an even or odd number of accepting paths. G is also contained in NLO for ZPPNP. This essentially means that an efficient Las Vegas algorithm with access to an NP oracle can solve graph isomorphism so easily that it gains no power from being given the ability to do so in constant time. G-complete and G-hard problems. Isomorphism of other objects. There are a number of classes of mathematical objects for which the problem of isomorphism is a G-complete problem. A number of them are graphs endowed with additional properties or restrictions. Digraphs. Labeled graphs, with the proviso that an isomorphism is not required to preserve the labels, but only the equivalence relation consisting of pairs of vertices with the same label. Polarized graphs. Two-colored graphs. Explicitly given finite structures. Multigraphs. Hypergraphs. Finite automata. Markov decision processes. Commutative class 3 nilpotent semigroups. Finite rank associative algebras over a fixed algebraically closed field with zero squared radical and commutative factor over the radical. Context-free grammars. Balanced incomplete block designs. Recognizing combinatorial isomorphism of convex polytopes represented by vertex-facet incidences. This list is incomplete. You can help by expanding it. G-complete classes of graphs. A class of graphs is called G-complete if recognition of isomorphism for graphs from this subclass is a G-complete problem. The following classes are G-complete. Connected graphs. Graphs of diameter 2 and radius 1. Directed acyclic graphs. Regular graphs. Bipartite graphs without non-trivial strongly regular subgraphs. Bipartite Eulerian graphs. Bipartite regular graphs. Line graphs. Split graphs. Chordal graphs. Regular self-complementary graphs. Polytopal graphs are general, simple, and simplicial convex polytopes in arbitrary dimensions. This list is incomplete. You can help by expanding it. Many classes of digraphs are also G-complete. Other G-complete problems. There are other non-trivial G-complete problems in addition to isomorphism problems. The recognition of self-complementarity of a graph or digraph. A clique problem for a class of so-called M-graphs. It is shown that finding an isomorphism for n-vertex graphs is equivalent to finding an n-clique in an M-graph of size n2. This fact is interesting because the problem of finding an clique in a M-graph of size n2 is NP-complete for arbitrarily small positive epsilon. The problem of homeomorphism of two complexes. G-hard problems. The problem of counting the number of isomorphisms between two graphs is polynomial time equivalent to the problem of telling whether even one exists. The problem of deciding whether two convex polytopes given by either the V description or H description are projectively or affinely isomorphic. The latter means existence of a projective or affine map between the spaces that contain the two polytopes, which induces a bijection between the polytopes. Program checking. Manuel Blum and Sampath Kannan have shown a program checker for graph isomorphism. Suppose P is a claimed polynomial time procedure that checks if two graphs are isomorphic, but it is not trusted to check if G and H are isomorphic. Ask P whether G and H are isomorphic. If the answer is yes, sir, attempt to construct an isomorphism using P as subroutine. Mark a vertex U in G and V in H, and modify the graphs to make them distinctive. Ask P if the modified graphs are isomorphic. If no, change V to a different vertex. Continue searching. Either the isomorphism will be found, or P will contradict itself. If the answer is no, perform the following 100 times. Choose randomly G or H, and randomly permute its vertices. Ask P if the graph is isomorphic to G and H. If any of the tests are failed, judge P as invalid program. Otherwise, answer no. This procedure is polynomial time and gives the correct answer if P is a correct program for graph isomorphism. If P is not a correct program, but answers correctly on G and H, the checker will either give the correct answer, or detect invalid behavior of P. If P is not a correct correct program, and answers incorrectly on G and H, the checker will detect invalid behavior of P with high probability, or answer wrong with probability 2-100. Notably, P is used only as a black box. Applications: in cheminformatics and in mathematical chemistry, graph isomorphism testing is used to identify a chemical compound within a chemical database. Also, in organic mathematical chemistry, graph isomorphism testing is useful for generation of molecular graphs and for computer synthesis. Chemical database search is an example of graphical data mining, where the graph canonization approach is often used. In particular, a number of identifiers for chemical substances, such as SMILES and INCHI, designed to provide a standard and human-readable way to encode molecular information and to facilitate the search for such information in databases and on the web, use canonization step in their computation, which is essentially the canonization of the graph which represents the molecule. In electronic design automation, graph isomorphism is the basis of the layout versus schematic circuit design step, which is a verification whether the electric circuits represented by a circuit schematic and an integrated circuit layout are the same.